Viewers like you make this program possible. Support your local PBS station.
Gemstones, precious metals, and power. Building blocks of civilization. But how are they created?
Our Earth is a master chef. She knows how to cook.
These gems are really forged in unimaginable conditions deep inside the planet.
How did metals shape our past?
I love steel. It's actually the backbone of our society.
And how will these gifts be used to build the tools of tomorrow?
Such a simple element has enabled all of the technology that surrounds us today. It is amazing that this came from the sands in our deserts.
We're going to launch this incredible telescope, and we're going to send it 1 million miles into space from the Earth to actually unlock the secrets of the universe. And it will all rely on 2 ounces of gold.
In this episode, we go deep into the fuels that drive our world.
It's amazing that we can see it with our own eyes.
What are their secrets?
Look, this is what we've been looking for.
You're holding in your hand huge amounts of energy.
And what are their risks?
We're affecting our planet. Humans affect the planet.
Can we discover new treasures to satisfy our energy needs?
In this rock, there is an incredibly powerful untapped force.
If we just get it right, there's huge potential.
Treasures of the Earth. Right now on Nova. All around us, Earth's spectacular riches are on display. Mountains, oceans, and plentiful crops. But Earth's bounty is not just skin deep. Some of our most important resources are forged even deeper inside our planet. These treasures are the fuels we depend on. They may not be beautiful, but they power our modern world. We use them to heat, to cool, to light up our cities. They drive our cars and propel our planes. They have allowed us to build our civilization. But what secrets are locked inside that give them so much power? And today, as we learn that some of these treasures are affecting our climate and pose a threat to our survival, can we find new treasures and new ways to keep the power on? The way to start finding answers is to trace the energy back from the plug on your wall. New York City, America's largest and center of its corporate and cultural power. Keeping the bright lights of this big city on is this man's job.
Any outages right now?
Nope, no sir. Craig Ivey, president of the power utility known as Con Ed.
Without electricity, the subway doesn't run, the elevators don't run. New York is the financial center of the world, the media capital of the world. We have to maintain reliability in this city. This is the nerve center.
So I want to get that expedited.
So everything going on within the grid is monitored 24/7, 365.
Here, in Con Ed's master control room, experts keep a close eye on the network of cables, transformers, and power stations that deliver the city's electricity, called the grid. As New York heads into summer, when air conditioners run full blast, this nerve center gets even busier.
This can be an exciting place.
Well, they found a defect in the transformer.
This is a serious-minded group all the time, but on those peak summer days, the intensity ratchets up.
Brucey, how are they doing on the 53 amp?
That's when the stress level inside this room goes up. You can't change summer. People want to be cool, they want to be comfortable, so therefore, when customers want it, we have to produce it.
The high demand for electrical power starts here, where you plug in your coffee maker, and computer, lights, washing machine, TV, and one of the hungriest of all, your air conditioner. That means Con Ed must provide 1 million watts of electricity continuously during peak hours, every few blocks. All that adds up to as much electricity as some entire countries. There are enough underground electrical cables in New York City to wrap around the Earth almost 4 times. At the end of those power lines is the source of all that electricity, a power plant. At its center is a massive 15-story high ball of fire.
Most people take power for granted, and until it's not there for them, do they realize how important it is.
Tommy Quartuccio is the director of the largest power plant in New York.
2,300 megawatts is what we could put out, about 22% of the power for New York City. So we're very important.
Ravensworth Generating Station, nicknamed Big Alice, was once the world's largest.
During the summer period, the units run continuously. The control room operators are around the clock. We're here 24 hours a day, 7 days a week, 365 days a year.
Despite the enormity of the task, supplying the electricity New York needs comes down to a relatively simple machine. First invented in the 1880s, a turbine. At its most basic, a turbine is something like a fan with blades turned by steam power. Its shaft spins a generator with magnets that create a flow of electrons. That flow of electrons is electricity. What generates that steam? Well, that depends.
Steam turbine just needs steam. It swallows steam no matter what it's made from, any type of fuel, coal, natural gas, or oil.
The turbine doesn't care. It all comes down to what is available, cheapest, and most reliable. Today, Big Alice burns 99% natural gas in massive boilers.
This is where it all happens, right inside the boiler.
The boiler, 15 stories tall and 2,000 degrees, is a swirling ball of fire. This fire can consume 9 million cubic feet of natural gas every hour, a volume equivalent to more than 100 Olympic swimming pools. But natural gas wasn't always what made Big Alice run. When it first came online, it burned coal. Coal has been phased out in New York, and its use is on the decline across the U.S. as its environmental and health dangers become more apparent. But when New York City was built, coal was king. It is the fuel that built much of our country, partly because North America has the largest coal reserves in the world. In the near total darkness of a coal mine, you begin to understand why coal played such an important role.
Oh, here it is. This dark, black chunk of the wall here, this is where the miners would have come. And they would have worked in these dark and wet and cold tunnels to pull out this coal.
Liz Hajek, a geologist from Penn State University, says today coal produces only 1/3 of U.S. electricity. But in its heyday, it was our primary source of power. And this Pennsylvania coal was prized above all.
There's a bunch of different kinds of coal. There's brownish, lignite, bituminous, but this is anthracite coal. It's dark, it's shiny, it's almost all carbon. And it means it would have been really valuable to the miners that were coming down into the mine.
The mountains of Ashland, Pennsylvania, hold the world's largest known deposits of anthracite coal. But why? According to Hajek, the rocks above the mine give us a clue.
So this is shale. What we know, we can look at this rock and we can figure out what this landscape used to look like over 300 million years ago.
These rocks formed long ago, even before dinosaurs.
And in this case, we know that this shale formed in a swampy environment. Oh, look. This is what we've been looking for. Here, if you look closely, you can see this is a leaf. This leaf would have grown in these coal swamps. So these swamps would have looked like the Gulf Coast of the United States today, or maybe the Florida Everglades.
Over millions of years, those trees pulled carbon out of the air through photosynthesis, the way plants use sunlight and water to grow. When the trees died, that carbon got buried underground in the wet, swampy water. With pressure created from layers of earth pressing on them, those trees turned into coal. Anthracite coal can be more than 90% carbon. But what secrets are locked inside these ancient fossils that are the basis for so much of our modern world's energy? One way to see the power inside is to burn it, says chemist Andrea Sella from University College London.
Coal is one of the materials that has really changed our world. And that's because coal is made of carbon, and therefore we can burn it. Now, I can illustrate this by taking a bit of liquid oxygen. Now, the beauty of coal is that it doesn't react at room temperature. But if we start to warm it up in the flame until it's really glowing hot, and then drop it into the oxygen immediately, and it burns fiercely. What we're seeing is the release of energy as light and heat. When you hold a piece of coal in your hand, it looks incredibly unpromising. I mean, it's just this rough black rock. And yet, it's got an incredibly complex chemical structure. And in a sense, what you're holding in your hand is the equivalent of a charged battery.
How coal acts like a battery is revealed in its atomic structure. Carbon atoms form long chains and rings, bound to other elements like hydrogen. These are called hydrocarbons, remnants of those long dead trees. When heated, these molecules vibrate.
At low temperatures, molecules move or vibrate very, very sluggishly. But as the temperature rises, they move faster and faster and, in a sense, more chaotically.
The chaotic vibration when coal burns allows its carbon atoms to break free and bond with other elements, like oxygen in the air.
Burning is one of the most familiar chemical reactions in our everyday life. In many cases, a chemical reaction will release heat, release light, and burning is a very fast example of that.
Robert Hazen, director of the Deep Carbon Observatory, explains how the heat of a fire results from releasing energy stored in the bonds between atoms of the burned material.
Imagine you have two atoms and they're separated. So if you can cause them to come together, you may have to force them. You can build bonds, but those bonds have a tension, they have an energy, they're storing this potential. And if you heat them up, if you react them with oxygen, they can break apart, recombine, and in the process release that energy.
That release of energy is related to the structure of an atom. At its center is a nucleus surrounded by orbiting electrons. These electrons are what bond atoms together. A hydrocarbon chain, which has so many atoms, is packed with electrons.
Turns out that hydrocarbons store lots of concentrated electrons. They're all crowded together in these compounds, and they really don't like that particularly. So if you burn them, some of the electrons go off to this oxygen atom, some of the electrons go off to that oxygen atom, and the flame that you see, the light that you see, the heat energy that's produced, that's all the result of these electrons reorganizing. That's the process of burning. That energy is released, and that's how we power our society.
Burning almost anything releases carbon, but carbon-dense coal and oil release a lot. Carbon long buried, combines with oxygen in Earth's atmosphere and acts like a blanket, trapping heat. The rising levels of carbon in our atmosphere began with the introduction of coal in the mid-1700s. Coal was the fuel that drove an industrial revolution.
Coal was absolutely fundamental. There is no question but that the Industrial Revolution could not have happened. Without coal, we would be in a completely different place as a species.
Starting in the mid-1700s, engineers began creating new coal-powered machines that would soon change life throughout England and eventually around the globe.
The great majority of people would look back at the kind of lives that were being lived in the pre-urban world with something akin to horror. British philosopher Thomas Hobbes said lives were nasty, brutish, and short. Life was physically really difficult because the principal source of energy was human power. We had a few rudimentary windmills, some water power, and of course we had wood. And so humans looked for something else, and this black stuff, coal, which they'd known about for a very long time, they suddenly realized that this had the concentrated energy that they needed.
And in the 19th century, as we begin really to harness the power of coal, what we are able to do is to make an individual worker not just 3 times more productive, but 20, 50, 100 times more. One worker could make acres of cloth. They could produce huge numbers of nails. They could make beams of steel in a way that had never been possible before.
Coal didn't just transform the nature of work. It created jobs that built our cities and drove significant political and social changes.
In the societies that had gone before, the aristocratic landowning class effectively owned their peasants who were working for them. They weren't actually slaves, but really had very little freedom to do anything because they earned very little money. Then, when the workers moved into the cities, the whole political nature of society changed beyond all recognition.
If coal built our cities, another fossil fuel, oil, transformed them. Today, oil powers our planes, trains, and of course, automobiles, providing 40% of worldwide energy needs.
Oil is a more concentrated form of energy. You could have had a coal-fired car, but it would have had to have had a whole trailer of coal being lugged on behind it. The liquid form of the oil is much more convenient.
In fact, you'd need more than 100 pounds of coal to get you as far as a tank of refined gasoline, which is liquid, easily transported, and has a high energy density.
You can live for a day without gold, and I know you can live for a day without gemstones. But try living a day without oil in our modern world, and I think you'll notice right away how important it is.
Jan Gillespie, a geologist at Cal State Bakersfield, explains how oil was discovered in places like Belridge, California, one of the most intensely drilled oil fields in the world.
Hunting for oil is a lot like hunting for treasure. We learn to read the geology just the way someone would learn to read the treasure map so that we can find the oil.
On the edge of the oil field, Gillespie searches for clues that reveal where oil might be trapped close to the surface.
From the road, if you thought this was asphalt, you'd be right, but it's naturally occurring asphalt. This did not come from a roadbed. This is exactly the kind of thing that the early prospectors here in this area, the wildcatters, would look for to determine where to drill their oil wells.
Asphalt formed from the same process as oil, so it doesn't take Gillespie long to find what she came here for.
This is what we've been looking for. Thick California crudes. It's the energy that powers the modern world right here, coming out of the ground.
Every aspect of our lives is completely intertwined with our use of oil and coal. It has given us the energy to transform our world. And yet, all of this comes with a downside. And that comes in the form of this little molecule, carbon dioxide.
The impact of this little molecule is now global. Carbon dioxide in the atmosphere acts like a blanket, trapping in heat and increasing temperature. This NASA map shows global temperatures rising over the last century.
We know that the temperature is going to rise ever so gently. We can anticipate increased droughts, increased floods. We can expect our oceans to slowly rise. Now, the occasional flood, the occasional heat wave may not sound like much, but what are the impacts on our agriculture? What happens if food supplies become less regular, less stable? The changes in our atmosphere are going to have big consequences for us.
We're affecting our planet. Humans affect the planet. You can't have a society without energy, and you can't have energy without consequences and side effects.
Despite these consequences, old habits die hard, and our society seems addicted to fossil fuels. They still provide 80% of the world's total energy, in part because of their versatility and the conveniently stored power in the bonds of the carbon atom. And there is another refined product of oil that is indispensable in our modern world. We don't use it for power, but it's another illustration of just how versatile carbon is. Plastics. Over the last century, human ingenuity has figured out how to refine oil and drink from it, sit on it, build with it, and make money from it.
I just want to say one word to you. Just one word.
Yes, sir.
Are you listening?
Yes, I am.
Plastics.
Like the advice given in the film The Graduate, plastic transformed all of our lives.
There's a great future in plastics. Think about it.
The discovery of plastic was revolutionary. For the first time, manufacturing was not limited to products found in nature, like wood, metal, or ivory.
Animal, vegetable, and mineral. I hadn't thought of that before. Maybe this little thimble belongs to a kingdom all of its own. The fourth kingdom. The kingdom of plastics.
Plastics?
This kingdom of plastics is something Rabi Musa studies. She is an organic chemist who investigates how chemistry affects our culture.
Just thinking about our heavy reliance on plastics and the things that would be missing from our lives if we didn't have plastics. So as I look around my space, my reading glasses, gone. Computer, not there. The refrigerator might be missing, the water bottle, light fixtures. Oh, and all my makeup containers, you know, the lipstick and the mascara, out the window. Toilet seat, gone. Gosh, toilet seat. Imagine not having a toilet seat. Who wears jeans that are 100% cotton? You gotta have spandex in there. We can wear jeans we're not supposed to be able to wear, right? It's everywhere. It's pervasive.
So how do we get all these useful, solid things from soupy, smelly oil? The answer can be found, once again, in the chemistry of carbon.
Most of these hydrocarbon fuels that we use are made of chains of carbon atoms. And when we burn them, we break them apart into smaller pieces. Or, with simple chemical tricks, you can link them together into longer and longer molecules. Those are polymers, or the plastics that we use.
What better way to show this than with a plastic model of one of these molecules, called ethylene?
So this would be ethylene. You can change the chemistry of this, for example, by replacing one of the hydrogens with a different element, like chlorine. And so this would make this vinyl chloride. And you can connect many, many of these together to make polyvinyl chloride.
Polyvinyl chloride, or PVC, makes atomic models, and so much more. Pipes, doors, windows, bottles, your credit card, even punk rock fake leather pants.
The future will bring plastic fabrics wondrously fine, yet resistant to wear, wrinkles, and stains, even the hazards of washing.
The world quickly fell for plastic.
Yes, this is a dream of the future.
And while the original dream of making useful products cheaply has come true, plastic, for many, is also a symbol of careless waste and overindulgence.
One of the challenges with plastics is that the very attributes that make it so useful, it doesn't degrade. If you put it outside and the elements, nothing happens to it, it just sits there forever looking at you. These are the very things that make it problematic when it's out in nature, because generally speaking, it's not biodegradable.
Waste plastic could be burned for energy, but like coal, oil, and gas, it too would release its carbon back into the atmosphere. Throughout history, humanity has drawn upon the resources Earth provides. The discovery of bronze built empires, and steel changed our cities. But as with all treasures, they come with a price, and the environmental consequences of fossil fuels and their products have become unacceptable. Ironically, there is one fossil fuel that is seen as a way to mitigate some of the negative effects of other fossil fuels.
Natural gas is the cheapest fuel, and it's also the cleanest fuel. It's the fuel we like to burn the most.
Natural gas is found deep in the ground or distilled from oil, and is seen by many as a bridge to a cleaner environment. It is cheap, and it puts 50% less carbon dioxide into our atmosphere than coal. That is why it is the primary energy treasure used today at the Ravenswood Power Plant.
Natural gas is very important to New York City. It burns cleaner, keeps the unit cleaner, the environment cleaner.
Natural gas, oil, and coal hold power in their chemical bonds. But where did it originate? The origin of all this fossil fuel power is found millions of miles away in the greatest power source in our solar system, the sun, a ball of superheated gas. Within the sun, energy is born in an amazing reaction called nuclear fusion, a process where hydrogen atoms are forced or fused together.
Fusion is taking two smaller atoms and ramming them together to create a bigger one. And that's a difficult process. If you consider, for instance, two magnets, and you say, all right, I'd like to take these two north poles and put them together, those two north poles will repel.
Dwight Williams, a nuclear physicist from the University of Maryland, explains the key to overcoming that resistance is heat and intense pressure.
You have to overcome a lot of force. So the way you overcome the force of the atoms, you get an extremely energetic environment, a very hot environment.
The temperature at the core of our sun can reach an astonishing 27 million degrees. This process of fusion within the sun's core releases vast amounts of energy that we see and feel as sunlight, but does much more.
Sunlight comes in, it streams down, it forms plants, layers and layers of them are buried. They're transformed into very chemically reactive bonds. Bonds that burn, and so you produce flame, you produce heat, light, the kinds of energy that we can then transform to power our society.
The bizarre thing is, of course, that we can never see energy. We can never taste energy. We can't feel it. The only thing is that when it is transformed, it manifests itself, and we see its effects.
The ability to transform this long-stored energy is why fossil fuels are so dominant in our world. But it is also why they are a problem, responsible for environmental degradation and climate change. And some of our treasures are also finite and will run out. So the essential question today is, can we find new treasures or new ways to use old ones so we can continue to build our world but one that will be cleaner and safer for future generations? That is now a key scientific challenge our world faces. The good news is that there are many possible solutions. First up on everyone's list is the sun. Could it be our greatest energy treasure?
There's huge potential. If you look at the numbers, the amount of solar energy reaching the surface of the Earth is 100,000 terawatts. And the amount of energy that civilization is using for all of its purposes today is 17 or 18 terawatts. This makes solar energy enormously attractive.
Tapping into this attractive energy source cheaply is now the goal. And there is an unlikely resource now taking its place on our list of energy treasures. Sand.
Sand is an extremely unassuming material. After all, we played with it as children. And yet, within it is a substance which has changed all our lives. Silicon.
Sand is silicon and oxygen. Sella can free the silicon by putting it in combat with the element magnesium that wants oxygen even more. He then adds heat.
And after a few seconds, the magnesium becomes hot enough to react. And the reaction begins to spread all the way through the mixture. There it goes. What we've done is we've freed the silicon of the oxygen. Once the test tube is cooled, what we're left with is no longer the sand, but instead a dark and rather shiny, reflective material. This is the silicon itself.
In its pure crystalline form, silicon looks more like a treasure, but its real value comes when you shine light on it.
Now, silicon is what we call a semiconductor. And semiconductors don't conduct electricity all that well until you shine light on them. And suddenly, the electrons can move. And that opens up a whole universe of possibilities.
These possibilities are now being mined around the world. And one of the best places to see this new treasure in action is in China, at one of the leading manufacturers of silicon-based solar panels, Trina Solar. The challenge with solar energy is bringing down costs, which is done in part by increasing the efficiency of each silicon cell.
Technical innovation here are focused on increasing the amount of energy we get out of the light that hits a photovoltaic cell.
Chu Chongfeng, the chief scientist at Trina Solar, says over the last 5 years, the number of solar panels has increased globally on average of 25% a year.
Our main goal is to lower costs so that we can be competitive with traditional sources of energy like fossil fuels. Maybe become even cheaper. Only in that way can photovoltaics become widespread.
The basic science of photovoltaic technology is straightforward. It's been around since the 1950s. Photo means light. And so when a photon of light hits a silicon atom, its energy knocks an electron loose, which is then directed through the silicon to the thin wires on the cell. That stream of electrons is electricity that can power anything from your toaster to your TV. Until recently, solar energy could not compete with fossil fuels because it was expensive. But that is changing quickly. There are many ways solar power is being made more efficient. Feng gives one example of how that is happening.
During the manufacturing process, metal lines that work as wires are printed on the surface of the silicon, but those metal lines cannot be made very narrow, which ends up shading quite a bit of the solar cells.
So scientists are working to make the wires thinner and closer together. New designs like this make tiny increases in efficiency that have a big impact on lowering costs. But there is a fundamental problem with solar energy. What happens when the sun doesn't shine?
One of the ironies of energy is that it's not so much we're running out of sources of energy. We have huge sources of energy. The sun is an amazing source of energy, but you have to be able to store it so that you can use it. So something like coal stores chemical energy and you can burn it when you need it. But what about solar energy? How do you store that?
In Zhongbei, China, a site of the 2022 Winter Olympics, there is an Olympian effort underway to address this problem.
This is our smart transformer substation. We make electricity from wind and from solar energy on a very large scale. What is different about this power station is that we then store the excess power in batteries. It's a simple idea, but figuring out the best way to do that is important.
Han Man Liu is in charge of this ambitious project, building the world's largest rechargeable battery, not unlike the one in your cell phone. In fact, this massive grid-level technology comes down to a lot of little batteries all strung together.
This is one of our battery panels. It's made up of a series of smaller batteries. We connect all of them together in order to get a higher voltage and a higher power. Here is a sample of one of the battery packs. It's the equivalent to 500 iPhone batteries. Oh, and it's very heavy.
This one locker contains 21 battery packs, which is repeated locker after locker, row upon row. And that is just in this one room.
There are rooms full of batteries in all 5 of these warehouses. Altogether, right now, we have 20 megawatts of battery storage.
20 megawatts is enough to power 7,000 homes for a day. The idea behind the Zhongbei National Wind and Solar Energy Storage Project is to harness solar and wind power and then use this massive array of batteries to make up for the periods when there's no sunshine or wind. This steady output can be seen in the master control room.
This is a chart of our total energy output. The yellow line shows the power we generate from the solar panels, which of course goes up during the day. Oh, as you can see here, when the sun goes behind the cloud, our power drops up to 20%. But with a battery on standby, it can fill those gaps. So the total output, which you see in the top green line, remains relatively steady. What we are finding is that the battery power needs to be only a small percentage of the total output of the power plant in order to be effective.
A battery is an amazing device because what it does, it provides a source of electrons, that's electricity, and it's just sitting there ready to use.
The way a battery works is through a chemical reaction. At its simplest, a charged battery has one side crowded with electrons. The other side is short of electrons, with a barrier between them. If you connect a wire between the two sides, electrons will flow along it. That flow of electrons is electricity. Now, to make the battery rechargeable, like the ones here in China, you need to be able to run the chemical reaction in reverse to start the process all over again. The reaction can't be reversed in just any type of battery. That's where the element lithium comes in. You're probably carrying it around in your cell phone battery.
The thing that's so neat about lithium is it's so small. It's element 3. It's one of the smallest of all elements, and so can move through channels other atoms can't. That gives lithium a special advantage in the lithium-ion battery.
This is lithium, an important treasure in our modern world. The reason lithium works so well is in part because it has only 3 electrons. Its small size is what we exploit in a lithium-ion battery.
And then you can recharge it because the lithium ions are still there. You just move them back over and start over.
This one cabinet of lithium batteries could power About one home for one day. Then we can recharge it.
This large battery storage facility, made up of so many little batteries, is now only in its first phase. The plan is to keep building until it can store 70 megawatts, enough to power tens of thousands of homes when the sun does not shine. But Liu says one of the most important aspects of this project is that they are trying out different types of batteries. They have old-fashioned ones, heavy and cheap lead-acid batteries, like in your car. 2 megawatts of more complicated liquid batteries, and room after room of small lithium-ion batteries. Liu is particularly interested in trying to figure out which of these batteries are cheapest and most reliable. Important considerations, he says, if grid-level batteries are to become a new storage treasure.
We spent a lot of money and a lot of time building this battery power station because we want to use it as an example to give society a solution. You can think of it as a very big experiment for our future.
All around China today, there are experiments like the Zhongbei battery. One reason is a critical problem here: air pollution.
Well, it's a pretty smoggy day today in Beijing. You still see these kinds of days pretty often. There's really severe air pollution.
Alvin Lin is a climate and energy expert in China. He says that years of burning coal have been the major culprit behind China's bad air, with devastating consequences.
In China, there's roughly about 1.6 million premature deaths per year caused by air pollution.
China today is a paradox. It is the world's biggest carbon polluter, but at the same time, China is making a major investment in developing non-carbon energy alternatives. It now has the largest domestic capacity of wind and solar power of any country.
China is very willing to try and find solutions. It looks like they're actually going to double their solar capacity in one single year, which is a huge amount of new solar coming online.
Around the world, new technologies are being explored and new energy treasures are coming online. Along with solar, wind power is now the fastest growing energy source. Biofuels distilled from algae and plants are even beginning to power some commercial airlines. But in the global effort to limit carbon pollution, there is one treasure already in use that is getting a new look. Nuclear energy, which supplies about 15% of worldwide electricity, does not contribute carbon to the atmosphere. It's expensive to build nuclear power, and safety issues have made it controversial. But there is a new generation of nuclear plants under construction today that are engineered to be safer. At its core, nuclear power simply generates heat that drives a turbine. But the source of energy that drives most nuclear plants is one of the universe's most ancient, stored in the element uranium. Uranium is one of the oldest of Earth's treasures, created in the death of a star or a supernova. Remarkably, that power can still be seen today with the naked eye, if you have the right light.
Let's turn the lights off and take a look with the black light here. Oh, wow. Look at that. Look at that.
Taylor Wilson is on the hunt to find uranium. Wilson, a nuclear physicist from the University of Nevada, designed his first nuclear reactor at only 14 years old.
So what I'm holding in my hand is pretty incredible. This is the uranium ore. This is the uranium mineral. And what's happening is the UV light from this black light is exciting the electrons in the mineral to give off this beautiful, beautiful yellow-green color.
Uranium is the most massive atom found in nature, containing 92 protons. As Earth formed, those heavy atoms sank deep into the crust and mantle, out of reach. Unearthing uranium took a colossal, earth-shaking event.
23 million years ago, traces of these atoms were blown into the atmosphere and onto this landscape from a massive supervolcano. This massive amount of hot ash was deposited on top of bedrock and completely decimated the terrain. And that ash flow had uranium in it.
Over time, groundwater concentrated the uranium into these rocks. The power that was stored in the uranium is what we now unlock for nuclear energy.
Only a fraction of this rock is uranium, but in those uranium nuclei, there is an incredibly powerful untapped force.
Radiation emitted from uranium is what Taylor is measuring. It results from the large size and the inherent instability of the atom. The unstable atom releases subatomic particles from its nucleus, which you cannot see, but they are literally leaking out of this rock right now. With a little bit of help from a nuclear physicist, that invisible reaction can be revealed.
We're going to start with some uranium ore, and we're going to place this uranium inside of our cloud chamber apparatus. I'm going to pour some methanol inside the chamber.
Williams uses dry ice and a gas to create a dense, cold vapor inside the chamber. That vapor is just on the edge of condensing. So close, in fact, that any radioactive particles passing through that vapor should trigger condensation.
Let's hope this works. Can we see? Yes. We can actually see tracks of radiation. What we're looking at here are the particles as they're being emitted from the uranium as it decays. Each particle has what looks like a white, tiny fizzing cloud as its trail, just like the trail behind an airplane that's flying through the sky. And it's amazing that we can see it with our own eyes.
Uranium releases energy slowly and steadily, like we see in this rock. This is considered to be benign, natural radiation. But the powerful stored energy, the energy that goes all the way back to a supernova, gets released in large amounts when we split a uranium atom at a nuclear power plant. Inside the reactor's core, a neutron is smashed into the nucleus of an unstable uranium atom, splitting it in two and triggering a chain reaction. Successive controlled reactions unleash the power long stored in uranium and generate the heat in a reactor we use to make steam. That steam just turns a turbine that generates electricity. The potential of nuclear power is enormous. 1 pound of enriched uranium has more power than 3 million pounds of coal, and it does not release carbon dioxide into the atmosphere. Statistically, nuclear power is far safer than power from coal, but it has a big image problem. It was born out of weapons research, and when it goes wrong, it's on a frightening scale.
A hydrogen explosion has occurred at Unit 3 of Japan's stricken Fukushima Daiichi nuclear plant.
But despite the risks that Fukushima and similar accidents have revealed, there's optimism that nuclear power can become a safe and environmentally sound energy treasure.
Certainly Fukushima, Chernobyl, and of course nuclear weapons have indicated that nuclear energy is a bit of a genie that we've left out of the bottle. But you know, if we continue to develop the energy source, hopefully it's my hope that we can develop one that will save us from some big problems like climate change.
Considering the implications of coal and carbon-based fuels, nuclear energy is an amazing option. So as we have a push for green energy, nuclear is going to have a much greater role than it has in times past.
Our demand for energy appears unstoppable. In fact, energy demand is predicted to triple by the end of the century. So there is a desperate need to explore all of Earth's treasures, to help find the solutions.
People always are looking for the technological magic bullet, the one thing that if we just get it right will save us. There probably is no silver bullet. There may be a silver shotgun in the sense of a wide variety of advances which together will solve a large part of this problem.
Our society fails without a reliable source of energy or sources of energy. We need to find new ways of doing it. This is a great opportunity and challenge for a society.
Across the globe, the race to find those solutions is accelerating. Along with solar, wind, and new types of nuclear power, there are many new initiatives. Off the coast of Denmark, energy is being captured from ocean waves. In Algeria, carbon dioxide from a natural gas plant is buried underground to find ways to clean up fossil fuels. And in New York City, Craig Ivey and his team are working to change the electrical grid by increasing the use of renewables and making a multi-million-dollar investment in energy conservation. This is all part of a global effort to decrease the use of carbon-emitting fuels that are changing our climate, and to find new treasures of the earth to provide the energy we need going forward. In the end, those treasures will help define who we are as a civilization.
The Bronze Age is called the Bronze Age because it was the time in human history when people discovered how to use bronze. As soon as we worked out how to use coal, it became one of Earth's treasures.
When you think about the ages of human society, Stone Age, Iron Age, Bronze Age, Plastic Age, what are we now?
I'm not sure that there's going to be a material where people say that the modern age is the something age.
We're in the era of incredible diversity of materials. Hundreds of thousands of different materials, all with their specialized characteristics. I think that's what defines who we are today.
Be more PBS.